Another common op-amp circuit that we need to be familiar with is called the inverting amplifier. In this circuit, we see that the input voltage is connected through a resistor that we call the input resistor to the inverting input terminal of the op-amp, while the non-inverting input terminal is tied to ground. The output of the op-amp is tied back to the inverting input through this thing that we call a feedback resistor. Okay, so now let's use the ideal op-amp model to look at what is the expected behavior, the voltage output behavior of this system. Alright, so again, the ideal op-amp model, if we use that, we're going to have Vn through the resistor Ri, and that's going to go into the inverting input terminal, V minus. Right, I'm also going to have that connected to Rf, and that's going to be connected to V out. Alright, our output terminal here is also connected to a dependent voltage supply that's referenced to ground. Alright, and the voltage of that dependent supply is some large gain factor times V plus minus V minus, the voltage at the non-inverting input terminal minus the voltage at the inverting input terminal. Okay, at the non-inverting input terminal, V plus, that is tied to ground, it's a reference to ground. Okay, so now we can take a look at how this system is going to behave. We know that the voltage at the non-inverting input terminal is 0, right? And we also know that since the output voltage is directly connected to this dependent voltage supply, that V out is going to be equal to A times the voltage at the non-inverting input terminal minus the voltage at the inverting input terminal. But because we know that the voltage at the non-inverting input terminal is 0, we know that this is equal to negative A, which is our large gain factor, times V minus. Okay? So the other thing that we need to do is we need to now establish an equation that relates the voltage at the inverting input terminal to these other voltages. Okay, and the way we'll do that is using Kirchhoff's current law. Right, so that we know that we have two current paths. Since we assume that there's an infinite resistance between the input terminals, there's no path through the op-amp. So the only two paths that we can have are current through the input resistor and current through the feedback resistor. Alright, so writing that from Kirchhoff's current law, we know that the voltage at the inverting input terminal minus Vn divided by Ri is going to give the current in this direction. Okay? And the current through the feedback resistor is going to be given by the voltage at the inverting input terminal minus V out divided by Rf. And we know that from the current law that has to sum to 0. Okay. So now what I would like to do is I'm going to separate these terms out here. I'll have V minus over Ri minus Vn over Ri plus V minus over Rf minus V out over Rf is 0. And also, what I'm going to do is I'm going to rearrange what I found previously, that V out is equal to the opposite of this large gain factor times the voltage at the inverting input terminal. And from this, I see that the voltage at the inverting input terminal can be rewritten as being negative V out over that large gain factor. So now, anywhere I see this inverting input, or excuse me, this voltage at the inverting input terminal, I can replace it with this. So doing that gives me negative V out over A times Ri minus Vn over Ri plus, alright, plus minus, so this will be also a negative V out over Rf times A minus V out over Rf is equal to 0. Alright. Now I'm going to separate all of my outputs and inputs. So, and I'm going to bring all of the outputs over to this side. So I will have negative Vn over Ri is equal to V out. Now remember, all of these will become positive because we're going to bring them to the other side. 1 over ARI plus 1 over RFA plus 1 over RF. All right, so now is going to be a good time to use the trick. Remember that we are assuming that the gain of the op amp is nearly infinite. And if I assume that in the limit that a goes to infinity, these terms, these denominator terms, are going to become very large, which means these terms that have a in the denominator are going to approach 0. So if I make that high or nearly infinite gain assumption, then we're left with negative Vn over Ri is equal to V out over Rf. Okay, so rearranging this, I wind up with V out is equal to negative Rf over Ri times Vn. All right, and that is the equation that tells us how the output voltage is related to the input voltage of the of this configuration, which is called the inverting amplifier. All right, it's called an inverting amplifier because if I have a positive input voltage, then my output voltage is going to be negative. It's going to be in the opposite direction. So that's the inverting part of that. And the amplifier comes from the fact that we're going to multiply this input voltage by this factor RF over RI. So the magnitude of the resistor that's in the feedback path is going to, relative to the resistance on the input path, is going to determine the gain factor, or how what type of multiplication factor we're going to have. Now, it's important to keep in mind that this amplifier is still limited by the limitations of the inputs, the input power supplies. So the inverting amplifier still cannot provide an output voltage that is greater than or less than the supply voltages that are providing the power for the op amp. So if we were to draw a plot of what this looks like, right, our V out as a function of V in, and let's again say that we're this is our positive supply voltage, and this is our low side rail, BSS minus. All right, so when we have a positive input voltage, our output voltages are going to be negative, and it's going to be the opposite. When our input voltage is negative, our output voltage is going to be positive until we reach the rails, or the power supply. Right? And at that point in time, the amplifier is no longer going to amplify. It's just going to provide either the maximum output or the minimum voltage output. All right, so our plot of what this would look like would be a linear relationship until it reaches the until the output reaches the maximum value or the minimum value that's determined by the power supply provided to the op amp.